Good morning. Today we'd like to continue on the chapter of kinematics. Last time we start talking about how to describe the flow. We talked about different way of describing the flow by the streak line or streamline or path line. And we start talking about also the Renal's transport theorem to transfer between information on the control volume and get information on the control mass or the material element. The mass conservation equation in the integral form is actually the Renal's transport theorem with extensive property capital B equal the mass and the intensive property small b equal 1. So since the mass is constant, so for a particle, for a control mass, for a material element, dm by dt is 0. So accordingly, we have this equation as the integral form of the mass conservation. The first term is partial t, the mass within the control volume, how this will change with time locally. And then we go around the surface, every velocity, normal to the area. So we got V dot dA, we get the volume flow rate multiplied by the rho density, we get the mass flow rate. Please note that the mass out will be positive since the component of V will be the same direction as dA. The mass in will be negative because the velocity vector will be in the opposite direction of A. So accordingly, we have negative contribution for inlet flow, and we have a positive contribution for the exit flow. Okay. Now, we would like to reach differential equation for the mass conservation. Maybe the question comes, when do I need to work with differential form? When do we need to work with integral form? If we would like to know about certain point in the domain, certain x and y and z and at certain time, for this point, we look for differential form. If we would like to have a global mass out, a global mass in, or mass change within the control volume, we'd look at the integral equation. Now, we use the diversion theorem to convert the surface integral rho v dot dA into a volume integral. By the diversion theorem, the integral of the vector rho v dot dA at the surface equal the integral divergence of rho v for the volume. Please note that the control surface should be completely surrounding the control volume. I mean, this control surface should be completely surrounding this control volume. Now, we have all terms with integration with respect to dV. Since this dV is arbitrarily constant, arbitrarily chosen, we can just consider the integrand to satisfy the equation. The integrand here will be dρ dt, and the integrand here will be del dot rho v. So accordingly, we get the general form of the mass conservation, partial rho partial t, the divergence of rho v equals 0. This is the general mass conservation equation, continuity equation for any flow, whatever the situation is. I would like you also to know the word divergence. Divergence means del dot. Since the del is d by dx in I direction, and del in y direction would be partial y, and in direction z, partial z. And this is a vector operator. When it applies on rho v, which is also a vector, sometimes we call it mass velocity. Rho v is a mass velocity. Accordingly, we have del dot rho v will be d by dx rho u, d by dy rho v, d by dz rho w. Since I dot I will be 1, but I dot j will be 0, I dot k will also be 0, and then we have this form. In Cartesian coordinates, we can see in the Cartesian coordinates, we can see that this will be the mass conservation, partial rho, partial t, d by dx or u, d by dy or v. Please note that rho is inside the derivative sign. I mean, this is general, rho can be function of time, rho can be function of space, and accordingly you have this general mass conservation equation. I would like you also to know about the substantial derivative, d, capital D. Capital D means for fluid particles. So we can consider the derivative, the substantial derivative, the derivative following a fluid particle. Sometimes we call it Lagrangian derivatives. Dρ by dt equal partial rho partial t. This is at local point, certain x, certain y, certain z, plus dρ dx by t, and dx by t is u. And dρ by dy by t, which is dy by t is v. Dρ by dz by dt, or dz by t is w. Accordingly, we have this form, partial rho partial t plus v dot del applied on rho is the total derivative or substantial derivative of density with respect to time. This is one form of the mass conservation, general form of mass conservation. Okay, I show you the gradient here. Gradient means del only. Del dot is a divergence, and del cos it curl. You know the cross product and dot product. Del without any point or x is just a gradient, okay? And the gradient of a scalar is a vector. Well, later on maybe you'll know that's the gradient of a vector is a second order tensor, and so on. The gradient increases the order of the tensor one. I mean, if you have a scalar like pressure, the gradient of the pressure is a vector. So the gradient increases the level from zero order tensor, which is a scalar, to one order tensor, which is a vector. The opposite is a diversion. Diversion is del dot. Diversion to a vector is a scalar. So the divergence velocity vector is scalar, and it appears here in the mass conservation because the mass conservation is a scalar equation. It's not a vector equation. هي معادلة لكمية قياسية, which is the mass, الكتلة يعني. Okay. Now, I would like to define the acceleration of fluid particle. Okay, the acceleration is the derivative of the velocity in general. But now we are looking for fluid particles. So we are looking for substantial derivative. So AX, for example, will be capital du by dt. AY would be capital dv by dt. Acceleration اتجاه z, AZ will be capital dw by dt. And as an example here, I have that acceleration in direction of x, partial u, partial t, where x and y and z are constants. That's a local acceleration, plus u du dx, v du by dy, plus w du by dz. This is the transport acceleration or convective acceleration. Notice for solids, we don't have this convective acceleration. For fluid, since the flow is moving, we have u, we have v and w. We have variation of u with respect to x, we have variation of u with respect to y, and accordingly, we do have convective acceleration for a fluid particle. When I say acceleration, I mean both local acceleration and convective acceleration together. I have here a simple, very simple example to show you the idea of the local acceleration. We have a nozzle. The nozzle is an apparatus or a duct that increases the flow velocity. Why? Sometimes, like in fire distinguishing equipment, we need a high-speed jet to reach some places and so on. So the nozzle is something that increases the velocity. But since the density is constant, so the increase in the velocity here is mainly because of the reduction of the area. Because when we apply the mass conservation, the flow in will be minus rho A1 V1, the flow out will be plus rho A2 V2, and the summation should be 0 because this case is a steady state. And accordingly, we have A1 V1 equal A2 V2 for incompressible flow. This is only for incompressible flow. That means the flow has a constant density. Okay. Now he would like to know, he has the velocity in 4 meters per second, has the diameter in at 6 centimeter. The exit diameter was 4 centimeter. As I told you, the exit area is smaller, so that we have higher speed. We can calculate the discharge. He wants to find the discharge, volume flow rate, the word discharge. The volume flow rate will be in meter cube per second. If I ask for mass flow rate, it would be kilogram per second, and in this case, we multiply by density. But here we have only the, we would like only to get the discharge. We would like to get the velocity exit, V2. We would like to have the acceleration, x direction. This flow is one-dimensional. I mean, the flow changes only in x direction. We have Q equal A1 V1 or A2 V2, and we calculate the discharge. It came to be 0.01131 meter cube per second, and multiply by 1,000 to be like 11.3 liters per second. To get V2, we divide Q by A2, or V1 A1 divided by A2, and accordingly we have the exit velocity equal 9 meters per second. Okay. Now I would like to look at the acceleration here. AX in general will be partial U partial t plus U du dx plus V du dy plus W du by dz. For this case, we have the flow steady. Accordingly, we have nothing change with time. So partial U partial t is 0 identically for this steady flow. Now U du by dx exists, but we don't have V. So we don't have V du by dy. We don't have W du by dz, since the flow is one-dimensional, and it's also one-directional. It's the one-direction means it has only one component in x direction. When I say one-dimensional, it varies only with x. The word one-dimensional, that means it depends only on x. That's why we say AX equal, in this case, U du by dx. Now with finite difference, I say du by dx would be V2 minus V1 divided by X2 minus X1, which is delta X. We get this way numerically, du by dx up to certain, that's proportional to delta X squared. Anyway, we have U, we get the average speed, V1 plus V2 divided by 2, as if we are calculating the acceleration at the midpoint of this nozzle. So we get V1 plus V2 divided by 2 is the average U in direction of X, multiplied by du by dx. Then the acceleration came to be around 270.8 meter per second square. For the special case of incompressible flow or constant, we have always, we can cancel the density variation. When I say incompressible, I just remind you, when we say incompressible, we get bulk modulus of elasticity goes to infinity. So for this case, we have, what's the special case for mass conservation? For the special case of mass conservation, we say, oh, constant. It doesn't change with time. It doesn't change also with the space. So accordingly, the equation will be considerably reduced. Du by dx plus dv by dy plus w by dz equals 0, or the divergence of the velocity vector is 0. Sometimes we call, for incompressible flow, the velocity vector is divergence free, is divergenless. That means without divergence, okay? For two-dimensional, nothing changed with z. We have partial u partial x plus partial v partial y, okay? Equals 0, which is very simple. I want to remind you, this is exactly satisfying the mass conservation when we use the stream function. You remember last time we talked about stream function when we said u equal d epsilon by dy and v equal minus d epsilon by dx, and the epsilon, or the difference in epsilon, better way, the difference in epsilon represent the volume flow rate between the streamlines. And epsilon has a constant value on each streamline, okay? Now, if we remove u, put partial psi, partial y. If we remove v and put minus partial psi, partial x, this equation identically zero. Why? The order of the differentiation doesn't matter. I mean, d2 psi dy dx equal d2 psi dy dx dy. So accordingly, we have zero identically. So the use of the stream function satisfies the mass conservation equation identically. So if we solve for a stream function, you don't need to use mass conservation equation. It's already satisfied by having definition that u equal d psi by dy and v equal minus d psi by dx. I would like you to calculate for this example. We had less time. If u equal minus, v equal minus 2y and u equal plus 2x, we can calculate ax and ay by using ax equal u du by dx, v du by dy. I would like you to notice that v is zero everywhere, so v du by dy will vanish. We look at ay, u dv by dx plus v dv by dy. Dv by dx is zero, but u has value, but dv by dx is vanishing. So we can get ax equal 4x meter per second squared, and excuse my mistake here, ay equal 4 meter per second squared as well. This is a mistake here, please notice this. Okay, this is our trial way for this lecture, very small, but I would like to make sure that all of you would follow this lecture well. I hope so, okay?